Good morning, dear. Today is 2nd October 2020, and we are going to discuss about support vector machine, a new topic, a new kind of classifier. Okay. Uh, so far, you have understood many classifiers. Okay, there's logical regression, naive Bayes, and under naive Bayes, there are three classifiers we have studied. So this is another support vector machine is another classifier. So what is big deal? We can ask, right? It is a big deal because support vector machine is altogether a different kind of classifier based on far more sophisticated ideas compared to the previous classifiers, according to me and according to many people. Okay, because this is although this is a linear classifier, binary linear classifier, but as you know, binary classifier can always be used for classifying multiple classes. Okay. Say, again, I am repeating, suppose you have classes like mango, banana, orange, and you need to classify them. Okay, so first, if you want to use a binary classifier, classify between mango and rest of the fruit. Banana, if you want to classify banana and rest of the fruit. Like that, multiple classes using binary classifier can be classified. And inherently, this is linear classifier. However, there is a concept called kernel um, function, which we discussed, which is very strong point about support vector machine. Using that, this can be used as a nonlinear classifier. Okay, although inherently it still remains linear classifier. So that magic we'll discuss also. And one more specialty about support vector machine is this is the first time a classification problem, perhaps first time, a classification problem has been modeled as a constrained convex optimization problem. Okay. Now let us try to just go through some interesting history. So credit of inventing support vector machine primarily goes to Vladimir Bapnik because in 1974, so this is Vladimir Bapnik in 1974 for his PhD thesis. He developed this concept that how classifier can be modeled as a constant convex optimization problem because convex optimization problem there are so many solvers. Okay, also it is called quadratic optimization problem. There is QP solvers are available, theory is available, so we could utilize those things for our classification tasks. So that he introduced the concept, and again in 1995 he demonstrated after migrating from Russia to United States. In AT&T and Bell Laboratory he worked, and during that period of time, US Postal Service, they were trying to automate their mail sorting process. You know, those days we used to send a lot of physical mail. Okay. Uh, so, like our country, other countries also, everywhere physical mail used to move. Okay, messages were carried by physical mails, and it was a tedious task to sort them because every mail had a unique pin code which is normally written by hand. So those are the digits. Okay, so his classifier, support vector machine based classifier, was put to test against neural network and other classifiers from accuracy point of view and all. The support vector machine outperformed others, and there was no stopping. Um, During those period, late 90s, support vector machine was completely dominating the neural network. The reason we'll talk. Okay, so this is a little bit history. As a classifier, it is great. Okay, because it has the following characteristic feature. You see, support vector machine creates a maximum margin between classes. Okay, say I have uh, I will give an example to class problem. Say I have some negative class samples and positive class samples. So support vector machine, what it does, it first try to figure out support vectors, and this is the decision boundary. So these are the two classes. For example, in neural network, another classification task, if you try to solve this problem using those tool, then you will get a decision boundary like this, or it could be like this. Okay, but maximum margin inherently is not guaranteed in other classifier. Okay, but here this classifier, this is the maximum margin between the decision boundary will be drawn. The structure of the model is such that the decision boundary will be drawn keeping maximum margin from both the classes. And what is the advantage? Advantage is, for after designing, if you use it for classification, then it will be more robust because misclassification will be minimized, right? Because this has tolerance, means even some samples are here and here, it will still classify they belongs to positive class. Similarly, if some samples are here and here, still it will classify that those belongs to negative class. So maintaining a maximum margin is important, and support vector machine focused on that criteria, which no other classifier inherently or structurally can guarantee you, but support vector machine can guarantee you. Okay. It has, then we will talk about what is primal problem. Then we will try to understand how to solve the primal problem, and how to understand the solution process by solving a problem by hand. Then we will talk about why primal problem is not sufficient. So we will talk about dual problem formulation. Okay, and again, primal problem and dual problem equivalency has to be first checked before replacing primal problem with dual problem. Otherwise, there will be a mistake. And that checking can be done by so-called KKT condition. We'll discuss about that. Then we'll talk about how support vector machine can be used for nonlinear classification tasks using kernel method. And in that context, we'll discuss about kernel function and all. And then a group of scientists from Microsoft Research developed an algorithm, very powerful algorithm called ASUMO algorithm, which actually made support vector machine so popular. Well, so let us start our journey. So you see, what do you mean by maximum margin classification? Say here I have a class 1, I have some samples belonging to class 1, and I have some samples belonging to class 2. Okay, and this is just like a gutter, and on the halfway actually the decision boundary is passing. Okay, so this is called support vector machine because these are support vectors. Okay, if I consider this as a structure, okay, so maximum margin classification we have understood. Now if this is more illustrative, say if I now consider this entire gutter, which consists of this line and this line, just like a road you can see, as a structure, then this structure is actually developed by some support vector which belong to both the classes. Who are support vectors? Support vectors. Okay. Support vectors are those samples which are at the extreme boundary of that class. So if it is negative class, all the samples belonging to this class, and at the extreme boundary, the samples are here and they can be qualified to call it a support vector. Similarly, for this class, those samples which are at the extreme boundary of that class can be considered as support vectors, and we are only focusing on those support vectors for developing our model. Okay, and here the parameters are actually a little bit different, which you need to know. First of all, this is again a discriminative model. That means, and we will be, so that means the structure or the support, the decision boundary will be drawn by taking care of discriminating between the two classes. So this is a discriminative model, not a generative one. Number two, this is trained using supervised learning technique. So far all the classifier which you have studied are actually supervised, they are trained using supervised method. So you need label data. That means I need data of both the classes. Okay, this belongs to class 1, this belongs to class 2, like that. I need to have that. And the class level is indicated by yi, and yi belongs to -1 and +1. Not like earlier 0 and 1. Okay? In case of logistic regression, we had y level 0 and 1, but here this is -1 and 1. These are the two classes. Class are designated by this number, -1, +1. Clear? Then more so, you see here the parameter W is not weight parameter. Okay, there are two parameters W and B. B is actually bias. Okay, and we will see the origin of B. And this W, although is analogous to weight, but here it is not representing the weight. It is the parameter of the support vector machine model. And what the parameter is? The parameter is defined like this. Suppose this is my gutter, and W is a vector which is perpendicular to the gutter. And since the gutter and the decision boundary, they are parallel, because this is halfway between the entire width of the gutter. So this is also perpendicular to the decision boundary. Okay. So this is 2D example. So we are calling about a line. If it is 3D, means if you consider another feature, then it will be a plane. If more than those features, then it will be considered as hyperplane. Then you can only conceptualize, but visually you can see using two features. That's why I have drawn, and I will develop model using this particular diagram. So the structure like this, you see, if I now consider it as a structure, this is a, say, support vector machine. So this W actually is a vector perpendicular normal to this surface. Okay. So we need to fix up the parameter W. That means what is the length of the W, because depending on the length of the W, entire structure, think about a umbrella stick. This is an umbrella stick, and this is at the end of the umbrella stick, some structure like this is hold. Okay. So if I decrease this length W, then entire structure will come like this, come down like this. Okay. If I increase W, so the structure will also move. Structure means the decision boundary and the gutter together they will move. So determining W will actually fix up the structure, okay? And suppose samples are here or all around here, right? So negative class, positive class, okay? So where the decision boundary has to be fixed, W will decide in a great way uh, that, okay, that matter. Okay, so W is unknown, W is to be known through the model, okay? And here there is another parameter called B bias, and what is the intuitive essence of B? I'm going to tell you. Suppose this is my support vector, and this is my W. Okay. Now suppose here is an hinge. Okay, suppose, and I can rotate this. So the interstructure will rotate. Okay, and that means depending on the rotation at different places, so this is the bias will be there. So bias will determine the orientation of the structure, and W will determine the position of the structure, and in that process the complete structure will be obtained. That is the design of support vector machine, and once it is designed, then it can be useful for classification task for unknown samples. Now, why it is called machine? It is called machine because in physics, if you try to understand from physics, the machines are those uh, which can convert energy from one place to another place. Say, I have simple example. This is a Falcon point, okay, and I am putting some load, so W, and here, so if I put effort, here I will get the work, okay. So isn't it? So this is a machine. Okay, it's a lever. This is a machine. Example of a machine. In physics, that is the case. In support vector machine, it's a jargon term. Machine is term is attached with this. Reason is, so it is just like a clunky device. You give, so end to end, you give the support vector. So in a micro level, you give the support vectors, and the model will output this decision boundary. Okay, just like machine, you put some effort, what you will get. So give some support vector, define support vectors, and you will get, okay, the decision boundary. Also, from macro level, this is also can be called as a machine because this is a black, if you consider it as a black box, you have, once a machine is designed, you give unknown sample, directly you will get in which class it belongs. So, these are perhaps the reasons which, for which we are calling support vector machine. It's just like behaving like a machine. So having said that, what is so special about support vector machine? Support vector machine is designed using analytical methods. Okay, so analytical method. So again, go back here. Analytical method. So there are other methods. One of them is numerical method. Okay, so probabilistic method, the numerical method. Analytical method is the specialty of support vector machine. So this is an analytical tool. Okay, so far whatever classifier we have studied, their basis is not analytical. Okay, so the difference between these two, I will try to convince you with small example. Say, so this is quadratic equation. So all of you know how to solve this. Hmm, Let us put it plus so that minus b plus minus. So okay. So whatever it is, so let us put it 1. So two roots of this quadratic equations will be say minus b plus minus the power of b square minus 4 into a is 2 into c divided by 2a is 4. So these will be the two roots. Okay. This is analytical method of solving this equation. Now let us see, instead of 2, I put 1.5 plus 4 log x plus 1 equal to 0. Still there is one variable x, but this you cannot solve analytically. So you have to take the help of numerical methods. So you just know all these things, right? So f of x, you are trying to figure out for which value f of x will be 0, and you are trying to find that, so that point for which by iteration. Okay, so there are numerical methods, well-known methods actually which does this. So you start from some value of x, and iteratively you compensate that value till the function value changes its sign, and then you can be assured that your x actually lies between that changed value, and then you again refine your search and try to use search method, repetitive algorithm method, to figure out what is the solution for x. So this is basically numerical method, and this is analytical method. Okay. So analytical methods are always preferable because they are quick, okay, and they are easy to solve, and they are precise. So we will, in the next class, begin to develop a model with the background introduction which I have given to you. Hope this will be useful, and stay safe. Have a nice day, and goodbye.